Hello everyone, I am Aizon Edamitan, a third year BS Physics, and in this video I will explain my Python programming activity. So this activity covers several important Python concepts including basic calculations, functions and loops, floating point precision, machine epsilon, overflow and underflow, and floating point comparison. So let's get started. So for the part A, which is the basic Python programs. And for number one, we have the printing my name. So this is very simple Python program. So the print function is used to display information on the screen. So in this case, it displays my name. And for number two, which is the area and circumference of a circle, um, first we import the math module. The math module gives us access to mathematical constant and functions. Here we use math.py for the value of pi. And next is um, I put it here the formula of the radius, and this asks the user to enter the radius, and the input function receives the value as text. So we use float to convert it into decimal number. Then we calculate the area. So the formula of the area, same as with the formula of the circumference. And in the formula of the area, the two asterisk here and the two, it means the radius is raised to the power of 2. So finally, we display both results, the print area, print the circumference, and when we run the program, we enter a radius, and Python calculates the area and circumference for us. And for the number three, we create the which is the factorial and summation, and for here we create the function called factorial, and the keyword def is used to create a function, and the function accepts a number called n. So we start with the result equals 1, and for we use the for loop to multiply the numbers from 1 up to n. For example, if n is 5, the calculation will be 1 times 2 times 3 times 4 times 5, and it equals to 120. And then the return result sends the final answers back to the part of the program that called the function. Then we test the function using for n 5, 10, 20, and 100. This um, then we test the function using here and using the print here, the things here. And this calculate the factorial 5, 10, 20, 100. And we also calculate the sum from 1 to 1000 using a loop. And here is the total starts at 0. The loop adds every number from 1 through 1000. We calculate the same result using the mathematical formula, which is here. And the formula for the sum first and positive integers is here. Then these allow us to compare the results from the loop with the mathematical formula. So that would be for the part A. Now let's move on to part B. Here, this part here is we explores how computers represents decimal numbers and the limits of floating point numbers. We begin by importing numpy. So yeah, importing numpy as np. Then the numpy allows us to work with numerical data types such as float 32. And the machine epsilon for float 64s. And first, we calculate the machine epsilon for Python standard floating point type, which is normally a 64-bit floating point number. So x is equals to 1.0, steps equals to 0, and the while we start with x is equals to 1, and then while the program keeps dividing dividing by 2, and the purpose is to find the smallest value where um, adding half of it to 1 still produces a number different from 1. This demonstrates the precision limit of floating point arithmetic. And for float 64, the machine epsilon is approximately 2.22 times 10 to the power of negative 16. So this means that the float 64 provides very high precision for numerical calculations. For number 2, we have here the overflow limit. And we test here the overflow and we start x is equals to 1.0, then the while np and the x equals to 2, then here we keep multiplying by 2. Eventually, the number becomes too large for the floating point data types to represent. At that point, the value becomes infinity. This is called overflow. For the float 64, the largest finite value is approximately 1.797 times 10 the, to the power of 308. So this part demonstrates what happens what happens when a number becomes too large for the computer to store as a finite floating point value. Then we have here the underflow limit for number 3. This time, instead of making the number larger, we continuously divide it by 2. Eventually, the number becomes too small that it can no longer be represented as a positive value and becomes 0. This is called underflow. The smallest positive subnormal float 64 value is approximately 4.94 times 10 to the power of negative 324. So this demonstrates the lower limit of floating point representation. And next we have the um, float 32 machine epsilon. We calculate machine epsilon for a 32-bit floating point number. So the NP float function tells numpy that we want to use 32-bit floating point value. We perform a similar halving process as before. The machine epsilon for float 32 is approximately 1.19 times 10 to the negative 7. Finally, we compare the float 64 and float 32. Float 64 has a much smaller machine epsilon, which means it provides greater precision than a float 32. However, float 32 uses less memory and can sometimes be faster, so the choice depends on the applications. And so that would be all for the part B. Move on to the last part, which is the part C. Here we demonstrate an important problem with floating point numbers. So we check if zero point 0.1 plus zero point 0.2 is equal to zero point 0.3. Results equals 0.2, 0.1 plus zero point 0.2. Then we compare it with zero point 0.3. At first, we might expect zero point 0.1 plus zero point 0.2 is equal to zero point 0.3, but in Python, zero point 0.1 plus zero point 0.2 is equal to zero point 0.3 is false. Why? Because the reason is that the decimal numbers such as zero point 0.1 and zero point 0.2 cannot be represented exactly using binary floating point representation. So the computer stores an approximation of these values. And because of these tiny approximations, the result can be slightly different from the exact decimal value. That's why result minus zero point 0.2. This allows us to see the small floating point error. And repeated addition So we set here the expected is equals zero point 0.1 times 10,000 equals expected value is equals to 1,000. Then we calculate the absolute error. Then the absolute error is equals to total minus expected. So the absolute function gives us the absolute value of the difference. We also calculate the relative error. This um, this tells us how large the error is compared with the expected result. This example shows that even a very small floating point error can accumulate with the same operation is repeated many times. And that's the explanation for of my Python programming activity. In part A, we learned basic Python programming user input, mathematical calculations, functions, and loops. And in part B, we explored floating point limits, machine epsilon, overflow, underflow, and the difference between float 32 and float 64. And in part C, we saw how floating point representation can create small numerical errors, especially when working with decimal values like zero point 0.1 and zero point 0.2. And the main lesson is that computers do not always represent decimal number exactly, so understanding floating point precision is very important when doing numerical computations. And that would be all for my video, and thank you for watching.